Everyone, May the 18th. I am gone. Royally stuck with my research. Man, my data just doesn't make sense. I don't know what to do. People say when you do data analysis, garbage in, garbage out. This is what I feel like. I feel my data is garbage. And there's no way for me to even reason with it. This is just so hard, so impossible to reason with these data. Unbelievable. All right, anyway, let's do this. Is graph bipartite? No, it doesn't before. There is an undirected graph with n nodes where each node is a number between 0 and n minus 1. You're given a 2D array graph where graph U is an array of nodes that node U is adjacent to. More formally, for each V in graph U, there is an indirect edge between U and V. The graph has the following properties. There are no self-edges. There are no parallel edges. Graph U does not contain duplicate values. If V is in graph U, then U in graph V. The graph may not be connected, meaning there may be two nodes, such that there is no path between them. A graph is bipartite if the nodes can be partitioned into two independent sets, such that every edge in the graph connects a node in set A and a node in set B. Return true if and only if it's bipartite. It can be partitioned into two independent sets such that every edge in the graph connects a node in set A. This is a false. There's no way to partition the node into two independent sets. What do you mean by two independent sets? This is two sets, right? Such that every edge connects a node in one and another node in the other. I mean, if you think about it, a 0. Every edge has to connect to. So we have 0. And 0 is connected to 1, 2, 3. Because of that, 0 has to be in one side. 1, 2, 3 has to be on the other side, such that every edge is connecting from one to the other. But if we do that, then 1 and 2, there's no. So this is impossible. In this case, 0 connects to 1 and 3. So I can say 0 is in group 1, 1 and 3 is in group 2, group B. And then we'll look at 1. Now 1 and 0 we're already done. So 1 and 2. So 2 has to be in group B. And for 2, so we can partition. Basically, 0 and 2 are in one group. 1 and 3 are in the other group, such that every edge. Yeah. Okay, what do you think? Well, graph bipartite, group union fine. What do you think? Well, what I think is when you say, right, this is graph 0, node 0 is connecting to these, so they has to be. So everything here has to be grouping together, right? And we're looking here, everything here has to be grouped together. Now, when do we know things are wrong? Well, let's say we group these together, right? 1, 2, 3 are together. And then when you group 0 and 2. So we group 0 and 2. And we then group this. So we group everything. And in the end, there should be 2 groups, right? Because here, 1, 3, 0, 2, 1, 3, 0, 2. So there should be 2 groups. If in the end you see 2 groups, that means it's bipartite. If in the end you see more than 2 groups, or Smaller than 2 groups. Ooh, more than 2 groups. What it's asking for is every edge has to connect, right? Every edge has to connect, which means, can I have an empty? It can be empty, which means it is possible. Hold on. What if we have something? What if we have something? Let me add another edge, another node, but this node is by itself. Or even better, this is by itself, right? Let's add another one. So this is 4 to 5, 5 to 4. So basically we add another one just like this. Does that work? Interesting. I'm not sure. Okay, expected. True and true. True and true. True and true. Look at it again. If the nodes can be partitioned into 2 independent sets, such that every edge, yes, even if it's not connected, this edge is connecting these 2, so makes sense. Makes sense. So if it's connected, that should be already done. If it's not connected, how do we handle not connected? Well, all we want to know, so like if we do this, right? If we do this, then eventually we'll have 4 groups. 4 groups will work, right? 4 groups will work because we're basically saying we have 1 group and another group, right? And then whatever edges is connecting these 2 groups. Yeah, what we're saying is a group, right, means the nodes that are connected to somebody else. And if we have 2 groups, that means we have some nodes connected to something else, and I have other nodes, right? And if we only have 2 groups, then these 2 groups must be connecting to each other. And if we have another 2 groups independent from the original, then those will form. That will also be good. So if the total number of groups is even, right, we can keep writing, and I think it's still gonna be true. We can keep writing, like, let's say this is gonna be 6, this is gonna be 7, right? This will still be true. However, well, actually no, that should be 7 and 6. Okay, this will still be true. However, if we do this, that shall be false, because now we have even number of groups, odd number of groups. If we have odd number of groups, that means there's 1 group that does not have anything. I just said it, and it's so you're telling me that by itself it's fine. Is that an like edge case? Boom, how about this? We have 1 node, at least 1 node, right? Yeah, we have 1 node, that's it. Is 1 node a bipartite? 1 node is considered bipartite. Huh. Why? Because there's no edge. Because there's no edge. Makes sense. That does make sense. Every edge, so we all we need to consider is the one that has an edge. If it doesn't have an edge, we don't consider. Okay, that's fine. Now what we need to consider is because this, everybody is connected. So this basically is one group, right? So if I do this, okay, yes. So this is a connected. So basically this is one group. So we say it's bad. Now we're gonna add 1, 2, 3, 5, and 4. Right? So we have 2 groups. So this one gave me 3 groups. So let's see if 3 groups is good or bad. It should be bad. That should be false. So I think this will work. We'll do union find. We'll do union find and see how many groups do we have. If it's even, then it's gonna be good. If it's odd, then it's gonna be bad. So union and find. DSU. No, find first. Is not equal to x. Self.parent x equals self.find self.parent x. Path compression. X and y. Parent x. If px is not equal to py, blah blah blah, that will return false. No, it's larger than. False. Okay, then we say if self.rank px is larger than self.rank py, self.parent px equal, no, py equal to self.parent px. If self.rank px is smaller than self.rank py, then self.parent px equal to self.parent py. Wait, what? That's not right. It's just px. This is py. Else self.parent py equal to px. Self.rank px plus equal 1. And I'll return true. Alright, so that's that. DSU equals DSU land graph. Probably put n outside just in case. Okay. Then what do? We say for nodes in graph if nodes interesting. We need to remove the ones We need to remove the ones that are empty. Huh. I mean, because their parent. You cannot union yourself. Oh my god, I got it wrong. Shoot. My bad. Yeah, I was like, that doesn't sound right. Yeah. No, we skip, right? This is a parent itself. So after we're done with everything, and those are, yeah, so we remove the number of groups. Yeah, that's fine, that's fine. If nodes, I don't even need if nodes. We can just say, when you union everything, right? How do we do that? We just union 1 and 2, 1 and 3, and 2 and 3 will be union automatically. What we need to do is just for I in range 1 to len nodes esu.union nodes 0 and nodes I. Boom. Okay. And then what we can do is we need to find the total number of groups. So I can say groups equals a set. And for I in range n, groups.add dsu.find I. Right? And how do you know which is empty? Nodes with no edges. Nodes with no edges. We need to count. So if nodes, else nodes with no edges plus equal 1. So as groups, right? And then we shall return len groups minus nodes with no edges. Minus nodes with no edges. Then what? Then we need to mod 2. And we say has to equal to 0. What do you think? I have no clue. We accumulated lots of test cases though. You know what? Let's just try there. You wanna give it a shot? Okay. Wrong answer. Wrong answer. Output true, expected false. Okay, now we have a serious issue. Output expected false. What did I not consider? Alright, let's first see. Are there any nodes with no edges? No. So we can say groups 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I say it's good. But the answer is false. I mean, 0 goes out to all these. 0 goes out to all these. 0 goes out to all these. Maybe we need to see dsu.parent. Okay, 0, 1, 2, 3, 4. They are a group. Oh, all you did now is to find this is a group and this is a group, right? You find all these groups, but you did not establish that there are connections. Yeah, this is not right. This is not right. Because your goal is to make sure each... What I'm saying is, when you see this is already wrong, right? Because now 0 shall belong to a different group. Now these two, yeah, no, this is not right. Let's think again. So what we want to see is when these are connected. I mean, 0 is connecting to all this. Okay, that's fine. And then we go to 1. 1 of course connected to 0, that's okay. And 1 connecting to 2. That's okay, 1 connected to 3. Wait, hold on. We have 0, because each edge has to connect to 2 groups, right? So 1, 2, 3, 4, that must be a single group. And this group must be different from 0, right? So 0 shall not belong to the same group. But the next one, 0 belongs to the same group. And that's wrong. And how do you know 0 belongs to this group? How do you know 0 must be in a second group? Well, I mean, what I can do is put just 1, 2, 3, 4 in one set. Put 0 in the second set, right? The next one, we just see, because these should be put in the same set. When you say 0 is, we say 1 is 1 in a set. So 1 is not in a set. If there's something is not in a set, hold a sec. We can start from 0, right? And then we lead out to those nodes. And then 1 how do I, because 0 has to be on a different set, all right? Because 1 connects to what should I do? I feel like it's very simple, but I just got a little bit confused. Bipartite. If you have 0 to 1, okay, 2 to 1, you have 0, then we can do all these, all right? That's fine. And then 0 is 1, and the other one is another one. And you have the next one, 0 to whatever, and then 1 comes out. Doesn't matter you put which one, right? You can see if it's in this, if it's in one of them, right? Then whatever it has to be needs to be in the other. So if that is already in this, then it's false. If it's not, then we can just put, because if it's really bipartite, it doesn't really matter. You can flip back and forth. So in this case, I don't even think we need DSU, honestly. I don't think so. I think we just need an A and B, right? We just need a 2 set. And for I, nodes in enumerate, right? Enumerate graph. And if nodes, because if not nodes, we don't even consider that, right? If nodes, now, if I is in A, okay? If I is in A, then every node should be in B, right? Then for noding nodes, right? If node is in A, then you return false. Otherwise, d.add node. Else if I in B, so do the same thing. Now, if this is in B, then false. Otherwise, A add. Else, I is not in A, not in B. Then it depends on what the nodes are. Depends what the nodes are. Huh. How do we do this? Well, we shall set the node and see if there's any, you know what, this might be a better idea. Nodes set equals set nodes, right? Then we say nodes intersect nodes in A equals nodes set dot intersect intersection, right? Two, three. Yeah, intersection B. Yeah, so if this intersection A len larger than 0, right? Nodes in A is if it's larger than 0. Nodes in B equals the same thing, intersection B, right? We say if nodes in A and nodes in B, that is false. Because these are supposed to be only in one group. Now they are in separate, now they're in separate groups. That's Yeah, because these are supposed to be belonging in one group, there should be no connection between them. But if they are in two groups, that means there is connection between them. Then they shouldn't be, right? So they cannot. So they only belong to one group. Okay. If nodes in A, or if elif nodes in A, if I in A, then return false. It has to be in separate group. Okay. Else, if I is not in A, so nodes in A, okay, yeah, which was elif. Nodes, the nodes in A, so intersection has A, so all of them has to go into A, right? So if nodes is in A, it means it's not in B, but it's in A. And if I is in A, that's bad. But if I is not in A, then we can say A equals A dot union nodes, right? Because nodes is not in A, and I is not in A. And then we say B dot add I. That's a good case. Elif nodes in B. If I in B, that's gonna be bad. Otherwise, B equals B dot union nodes and A dot add I. Else, this is nodes not in A and not in B. Then we say if I in A, right? If I in A, then B equals B dot union nodes, node set. Damn it. Node set. Right. Else elif I in B, then A equals A dot union node set. Else I is not in A or B, then so nodes is not in anything, I is not in anything, then we just set I dot add A dot add I and B dot B equals B dot union node set. And we'll do this until the end, and then we'll return true. Oh, this one works for this, but let's see. Does it work for the others? My God. That was worse performance than last time. The hell? Expected true. Oh, it's not in a good shape today, huh? Alright, 0 to 3. We can draw. Let's draw. Apparently this one is not good. Alright, what do we have? We have 0 to 3, 1 to 2, 1 to 2, 1 to 4, 0, 1, 2, 2 to 1, 3, 3 to 0, 1, 2, 3 to 0, 3 to 4, and then 4 to 1, 4 to 3. So in this case, can we have bipartite? So 3 to 0 and to 4, 4 to 1, 1 to 2, like this. All right, 3, 0, 3, 4. Okay, that makes sense. It's bipartite. There's one group, there's another group. So in my case, I say 0, let's say 0 is A, 3 is B, okay? Next, 1 and 2, so I can say 1. Oh, I put 1 here, and I put 2 here, and 4 here. That is why it's wrong. Damn it. That's not the way to go. Dear me. That's a good test case, huh? What if we start with 3? Right? What if we start with 3? So let's say we start with 3. Then we know 0 and 4 must be on this side. Okay? Next, we can do 1. Oh, that's the problem. You shall find something. Okay, I think I know. So we start from 0, L connect to 3. Then we should look at 3, because 3 is all on this side. So 3 connect to 0 and 2. 3 connect to 0, already done. All connect to 4. Then we look at 4. 4 connect to 3 and connect to 1. Then we look at 1. 1 connect to 2, 4 connect to 2. And then boom. Yeah, you should just keep going. Which means we can do it. Maybe we can BFS or DFS it. Yeah, with the 0 and then we go this. Maybe we can DFS this thing. How do we DFS? So we start from this, and then we go, and then the next one has to be on the other side. But if it's already, yeah. See, this is not difficult at all, and we don't even have to return anything, right? It's just none. And all we need to make sure is we don't go back to the parent. We don't go back to something that's already been visited. How is it visited? If it's inside A and B, that means it's been visited, right? So now we are a node, okay? Now we are a node. So whenever we go to a node, what do? We check if it's in A or it's in B, right? If we say if node is not in A and not in B, then we put node in one of them, right? And then I'll go to that, my children, and the children has to be put in A or B. Children has to be put in A or B. And we can say if node is already in, then we don't visit it. So when we visit, hold on, what do you mean we visit a node? So we go to so we're at a node, right? We know which one it belongs to. And then we try to find its next, right? We try to find its next. And if the next is already visited, then we don't do it. If the next is not visited, then we visit it. But how do you know which one you shall force yourself to be? So set your group, right? It's gonna be a set, it's gonna be a group. So if you already in this group. This is the group which you're supposed to be, right? Well, we put you into this group. And then you shall say, oh, A and B. I think I need both groups. Group str. Right, so you should be going to this group, right? And if you're already there, then we're good. So if group str is equal to, why can't you just, because I want to check the other group. If group str is A and, wait, what should we do? We check it's not in this group. We just put them into the group. Yeah, we just put them in the group that they're supposed to be. Right? We just put them in the group that they're supposed to be. We say if node in group, which means they're already in there, then we return. Otherwise, group dot add node. But then which group is supposed to be? Groups. A and B. If node in, oh, that will be easier. A set and a set, 0 and 1. How do you check the other one? So your 0 group will be group index, will be an integer, right? If it's 0, we'll exclusive all with 1. 1 exclusive all with 0. Yeah, that's exclusive with 1. So if node is in groups, group index, then we're done, right? We don't keep going. Else, then groups, group index dot add node, okay? And then we say for child in graph node, DFS child group index exclusive of 1. Okay, and once we're done, we have two groups. We make sure that there's no overlap, right? Then we say for I in range n. Oh, we need to DFS it first. For this, yeah, we need to say DFS I and just put it in the first group. If it's already in it, then we don't do it. So we go through everything and then we say maybe we can do it right here. Right? If I in groups 0 and I in groups 1, we return false. Otherwise, we return true. How about this one? Dear God. What the hell? What? And it should be if it's already in one of them, then we don't do it, right? If I in groups 0, if I not in group 0 and I not in groups 1, then we do this, right? Then we do this. If it's in one of them, then we check if they're in both. Goodness me. Look at this stupid solution that I cannot figure out earlier. Yeah, this is not union find. Well, maybe it can still be. You know what? Let's don't jump into conclusion. Yeah, I don't know. This is so easy, but took so long. Unhappy. Definitely unhappy. My God. Definitely not a difficult one, but took me so long. I'm not in the best shape today. I started with DSU, union find, but that didn't work. Then I played around with sets, and yet the naive way of setting up sets also doesn't work. Then I realized that we have to traverse the graph and use set along the way. It works. O(n), well, the number of nodes we visit every single node. Only once. Okay, what was the other solution? That's exactly the same as this one. This must be a smarter idea. Coloring. Colors. Colors node. Check color. DFS. Every time you visit some node, the color has to change. Coloring. So that is the optimal solution. All right, let's try it. Oh. Use coloring. Each time we visit a node, change the color. Then we can decide whether the coloring is correct. Okay. N equals line graph. Colors equals 0 times n. Def DFS node color. Return a Boolean value. Right. Then we say if colors node turn colors node equals color. Right. So node has been visited. It must match the required color. Okay. Otherwise, then we say colors node equals color. And for child in graph node DFS child minus color. Yeah, because if your color is this color, your children must be a different color, right? And I'm going to say if not, right, then we'll return false. Otherwise, we'll return true. We've done this before. Then we say for I in range n, if not colors I, if not colors I and not DFS I, wait, do one color, then we'll return false. Otherwise, if it has a color, then we keep going, and we'll return true at the end. Coloring. Similar idea, right? Coloring is much easier to reason with. All right, took so long. I was trying to solve the other problem. We got stuck here. Yeah. No Ghana today, huh? I'll do it tomorrow. Well, I don't have Ghana today. All right, see you guys tomorrow. Adios.